Okay, here we go. Everybody back up here. Thank you. Everybody up here. Thank you. Okay, so in terms of the tests, you took them on Friday. I was away the whole weekend and I didn't get them until Monday, and then I was away Monday and Tuesday, and I looked at them, just the stack of tests, but I didn't actually look at any of them. So they're not anywhere near graded, but I promise I'll get them back on Friday. And again, that will include a snapshot of what your grade would be if the course ended right now. Okay, so that's coming up on Friday. Today, October 22nd, we are covering integer exponents. You'll recall that we talked about exponents last class. We started with exponents. And I didn't say this last time, but I'm going to say it today. So I've taught 096 here a bunch of times. And exponents is one of the toughest topics for students in this class historically. There are just so many different properties and then so many things that seem like they should be properties but actually aren't. And so really take your time and make sure you're trying to understand why things work in a certain way as opposed to just trying things that or writing things that seem true, because oftentimes things that seem true just turn out not to be true for exponents. They are tough. So we're going to go back to page 4, which is a page that we worked on last class already, but there's this chart at the top that had two properties in it, and we skipped one of them. So that's where we're coming back to. So the first property is the one that we talked about last time, is that a to the 0 is 1. In other words, any number raised to the 0 power is 1. And so we saw that before, but we skipped this other property, which has to do with negative exponents. So we'll talk about that property momentarily, but let's take a look at the last column in this chart, which I think right here, it says the pattern. So 3 to the 4th, everyone agrees, is 81, yes. And 3 to the 3rd is 27. 3 squared is 9. 3 to the 1st is just plain old 3. What did we define 3 to the 0 to be? 1, because we said over here any number raised to the 0 is 1. So far, so good. What we have yet to define is something that looks like that. 3 to the negative 1st power. 3 to the negative 2nd. 3 to the negative 3rd. We're about to define what those things mean. Negative exponents we're seeing for the first time. So, you know, I mean, like I understand that 3 to the 4th literally means 3 times 3 times 3 times 3, 4 copies of them, right? So like positive integer exponents are straightforward. You just list the number, the correct number of times. But what could it mean to say 3 to the negative 2? That is to say negative 2 copies of the number 3 multiplied together. It doesn't have the same meaning, and so it's kind of strange. So let's look at this pattern. How do we get from the number 81 to the number 27? What mathematical thing can we do to 81 to get to 27? We can divide by 3. Agree? And that makes a lot of sense because 3 to the 4th is 4 3s, but 3 to the 3rd is just 3 3s. So all we did was drop off one of those 3s by dividing it out. How do we get from 27 to 9? Is we also divide by 3. So of course, this is going to work all the way down. So then 9 divided by 3 gives us the 3. So far, so good. If you divide by another 3, you land on the number 1. That's super. But mathematicians really like patterns, and so we're just going to assume that this pattern continues as we try to give meaning to negative exponents. So what should we be doing to the number 1 to figure out what this next number should be? We should be dividing it by 3. And so 3 to the negative 1 we are defining right at this moment to just mean 1 divided by 3, third. And then what should we do to a third to figure out the next power? We should divide by 3 again. And so if you take 1/3 and you divide by another 3, we will get 1/9. And so we define 3 to the negative 2nd to be 1/9. And then divide by another 3, and we get our definition for 3 to the negative 3rd is 1 over 27. And so in general, let's actually do one more that's not on the page. But 3 to the negative 5th power, we kind of look at this pattern here. Do you guys agree that that 9 is just the 3 squared and this 27 is just the 3 cubed? And the only thing that's different is that it's on the bottom with a 1 on the top of the fraction. And so that's all we're going to do is define 3 to the negative anything to just be 1 over 3 to that same power. So 3 to the negative 5 is just 1 over 3 to the positive 5. That's how we define it. Just says divide by 3 the right number of times. So negative exponents really just mean put a 1 on top, shove the whole thing downstairs and make it a positive exponent. So 3 to the 5th, I think it's 243. Maybe somebody can check that for me. Yeah. So here's our definition in general. It's right over here. Is that if you have some power x, some base x, raised to the negative n, raised to any negative power, we just define it to be 1 on top of x raised to the positive power. That's our definition for negative exponents. And it turns out that if you have a negative exponent downstairs, like with a 1 on the top, and we think about kind of going the other direction, if it's a negative exponent downstairs, turns out it's just exactly the same as the positive exponent upstairs. That one isn't as clear as the first definition, I don't think, but it's a consequence. I'm not going to get into the details of it right now. But right here is our basic definition for how do you handle negative exponents. So we have this pattern just so we could kind of buy into this definition, but at the end of the day, it's just a definition. So let's go to page 9, which is where we start the new stuff formally today. And can we get Lydia to read the daily summary at the top? Thank you. So what we just saw from the basic pattern is that if you see x to the negative n, it really means 1 over x to the positive n. And then going the other direction, if it happens that you have a negative exponent downstairs, you just put it upstairs and you make it positive. So those are our formulas, but honestly, I don't memorize those formulas. I just understand that if there's a negative exponent, we move it. So this guy x to the negative 4, as soon as I see a negative exponent, I say, okay, that's a 1 over what? X to the 4. That's it. Nothing more, nothing less. X to the negative 4 just means 1 over x to the positive 4. And then in the next example, we see that there's a negative exponent, but where is it? It's on the bottom. And so where are we going to put it? Just on the top. So it becomes, I'm going to copy that 1 that's already up there, just in case it was something other than 1. But that x to the negative 5 downstairs moves to the top and becomes x to the positive 5, and that's it. We don't need to put the 1 there, but I'm just copying it because, for example, if it was 7 over x to the negative 5, the x to the 5 would come up. A lot of people would say, oh, the 7 goes down, but it doesn't. The 7 doesn't move anywhere. It has no reason to move. It just stays there. So that's why I copied the 1, but you don't need it. Okay, and now here's a third property, this x over y to the negative 7. It's a fraction to the negative power. You can apply the properties here in yellow, but I'm just going to give you a shortcut that I strongly recommend you just kind of memorize and use, is that if you have a fraction raised to the negative power, you flip the whole fraction and make it a positive power. So this one right here becomes y on top, x on the bottom, still in parentheses, but what's the new power? Is 7, positive 7. So I strongly encourage you to just start using that shortcut. Things get very messy if you don't know that shortcut. So if you have a fraction to a negative power, flip the whole thing, make it positive. All right, let's go to Kira for number 3. Keep going. Okay, so negative exponents we're now going to perceive as just representing motion. They move. Things from up on top of fractions move to the bottom. Things on the bottom move to the top. So let's take a look at this example here. We're going to rewrite that expression so it doesn't have any negative exponents. This is a very common like test or quest question. So here's what we do. The first thing I see is a 10. Does that 10 have any exponent on it? No. So is there any reason to move the 10? No. So don't go crazy just moving everything you see because there's negative exponents somewhere. 10 has no commands that say move me. R to the negative 9, it is negative, it has a negative exponent. So it moves. It is currently upstairs. Where does it move to? Downstairs, and it becomes R to the positive 9. That negative means move. As soon as you move it, you lose the negative. The next thing I see is D to the negative 7. It has a negative exponent, so where does it go? goes downstairs, it moves downstairs and becomes d to the 7. So I finished everything on top, everything that used to be on top anyway, and now we start reading the bottom. 25, does it have an exponent? No. So should it move? No. 25 stays right there. Next one we see is r to the negative 5th. That negative exponent means move. It is currently in the bottom, so it moves to the top, and it becomes r to the 5th. Good. And the last thing we see is that d to the 3. Does it have a negative exponent? No. So it doesn't move anywhere, just stays. It's really tempting to maybe say, okay, everybody moves, and d cubed was on the bottom, so it moves to the top, but it doesn't. It didn't have any directions on it that said move me. It's the negative exponent that says move. So this one stays down here as a d cubed. What's the advantage of the thing we just wrote down compared to the original? How is it better? Why is it simpler? No negative exponents. We got rid of all those negative exponents, and that is often a very good first step. Okay, so now we're so now we got to mush things together. So Julia says that if we look at the d to the 7 times d cubed, we had a property last time that said what do we do to those exponents? Was we add them. And so that's a d to the 10th downstairs, and that's as simple as the d part can get. Let's take a look at the 10 and the 25. Can we reduce that at all? We can. So 5 goes into both of these, 2 times on top, 5 times on the bottom, so it's going to be a 2/5 in our final answer. So just reduce those numbers as normal. Okay, and then we've got this r to the 5th on top of r to the 9th. So we do have a property. What do we do with those exponents? So we subtract them. Now if you do the top power minus the bottom power, 5 minus 9, we get -4, which is fine, but we're not allowed to have any negative exponents. So we would still have work to do if we did 5 minus 9. But what we can do instead is a nice little kind of shortcut here, and I encourage you to do this as well. I'm going to pick on Diana here. Diana, I think you explained this on at the last class at your table. What would you do? Like instead of doing the 5 minus 9, can you talk to us about what you did last class? Do the 9 minus the 5, because that's going to give us a positive power. And then where would we put these r's, Diana? Keep it at the bottom because there were more r's in the bottom to begin with, right? If you imagine actually listing these r's out, r, 5 of them, and then 9 of them down on the bottom, you would get rid of all of them on top, and how many would you have left over on the bottom? You'd have 4 left over, and they would be firmly in the bottom. And so my suggestion here is to not just like naively always subtract the top number minus the bottom number, but subtract the bigger one minus the smaller one. That way you'll get a positive exponent and you won't have anything more to do. The only twist is you got to make sure you put that thing in the right spot. Where do you put it? You put it where there's more. In this case, there are more r's downstairs. So downstairs we get r to the 4th, and that's our final answer. 2 over 5 r to the 4th d to the 10th. Okay, let's go to Tara for number 5. Okay, so scientific notation, looking at part A, says on a certain date back in 2012, U.S. national debt was approximately this crazy number here. That's 15 what? Anybody carefully read that number? 15 trillion and then a bunch of change. Certainly it's higher now. So let's just see if we can write this in scientific notation. So the idea is we need to write a number that is between 1 and 10. 15 trillion is far bigger than 10. So we imagine taking this decimal point and we just keep moving it until we eventually get a number that is between 1 and 10. So for example, if I decided to put the decimal point here, that would be 15 what? Million and change. Is 15 million between 1 and 10? No, but we're cutting this number down in size. What if I put it like right here? What number is that? That's like 1,500 and change, right? So it keeps getting smaller every time I just shove that decimal point farther and farther to the left. If I put the decimal point here, what number is that? 15, which is just a little bit too big. It's got to be between 1 and 10. So if we put it here, what number is that? 1.5, which is finally the number that's between 1 and 10. Yeah, let's go ahead and round this to 1.55. That seems reasonable. But the idea is you got to put the decimal point in the right spot, and there's only one right spot for any number. So this becomes 1.55, and then it's multiplied by 10 to some power. So what we have to do now is carefully count how many places did that decimal point move from its original location, which is purple, to its final location, which is red. One vote for 13. Can other people count? We'll just get some confirmation here. 13. Right, and the commas help you kind of count, right? So 3, 6, 9, 12, and then one more. 13 sounds good to me. So I'm going to put a 13 up here, and that's our answer. National debt, 15 trillion and change, could be written in scientific notation as about 1.55 times 10 to the 13. Okay? And let's take a look at part B, which talks about the diameter of a bacterium, and it's about 0.0000002 meters, really, really tiny. And we're going to write that in scientific notation as well. Now, if I take this decimal point and, keep moving it to the left, I'm making the numbers smaller and smaller, right? So we don't want to do that. Jasper? It is good. Yes, it's exactly right. We're going to move that decimal point to the right, and then we'll pay for it with a negative exponent. We have to go past the 2 because we need a number that's between 1 and 10. So for example, if you put the decimal point right in front of the 2, then you have 0.2, which is not between 1 and 10. So you got to keep going just one more past the 2. Let's do this one the same color as before, red, which puts it here. And the other one, we'll put it right here in purple. That's where it was. And so we're going to take our answer, write it in scientific notation. So at the moment, if the decimal point is in the red spot, then what number are we looking at? Just plain 2, super, times 10 to the, and then we count decimal places very carefully. And yeah, we moved 7 places, but it's negative because we went to the right, except I really would hate to have people like try to memorize, like if you move the decimal left, it's a positive exponent, and if you move it right, it's a negative exponent. I don't have that memorized. I only could say it right there because I was thinking of this example. All I know is this: if you have a positive exponent, like 10 to the 13, that's some massive, enormous number. And if I started with a massive, enormous number, like 15 trillion, then I should end with a massive, enormous number, like 10 to the 13. But 0.000002 is a really small number, really close to 0, and I just know that close to 0 is not massive. And so the not massive ones have negative exponents. So we'll just write that as our little shortcut over here. Technical term, massive number means you're going to have a positive exponent. Tiny number means you have a negative exponent. Okay? Yeah, so meters is not probably the best unit to think about something so small, but we wanted practice with scientific notation, so kind of artificially used a big length. All right, so there are not 1, not 2, but 3 activities that start on the next page. So see if you can work through all of those and raise the flag if you get stuck.